Lab 4 of the semester is titled the Oscillation Lab, in which a pre-made video of a ball of known mass was connected to a spring that was stretched and released while connected to a fixed axis. The movement of the ball was observed using tracker software, which was done in order to gain knowledge about spring constants and the energy principle related to spring. In order to analyze this lab properly, both the momentum and the energy principle needed to be understood. The momentum principle states that the change in momentum of an object is equal to the net force times the change in time. The energy principle states that the change in energy of the system is equal to the change in kinetic energy plus the change in potential energy, which is also equal to the work of the system. For the momentum principle, the F net is equal to the force of the gravity plus the force of the spring for this system, and the force of gravity is equal to 0, negative mg, 0, as its vector. The force of the spring is equal to 1/2 ks, the spring constant, times the stretch, and if the spring is at rest, the net force is equal to 0. For the energy principle, the delta K and delta U that are involved are the delta K of the spring, the delta U of the spring, and the delta U of gravity, and all these equations are shown above. The video given was uploaded into the tracker software and was calibrated to be 0.7 meters for the length of the initial spring. The axis was set so that negative y went in the down direction and positive x went to the right. You can see the data for the position versus time of the point mass up on the upper right of the screen and the data below that. In order to update this data into the computer code, the rest length and the value for k, the spring constant, had to be found. Based off of the equations known, k was rewritten to be equal to 4 pi squared times the mass times the period squared. The period was found to be 1.440, and then the k was found to be 7.64 newtons per meter, which was 12% off from what is known to be the value for the spring constant. The L naught was found based off of this spring constant and was found to be 0.184 meters. Since both of these values are significantly different from those that are known to be true, the known values were used for the computational code shown next. Here you can see the updated glow script code. The mass was set equal to 0.402 kilograms. The position and velocity were updated based off of the initial from the tracker software. And next, the values for T and delta T. These were not changed because the ones from the starter code were valid enough to keep. The G was set equal to 9.8 newtons per meter. The KS and LO are from the video, the known values. The L, L hat, and S were all set equal to what is known about springs. Based off the equation shown earlier, the K, UG, US, and E were updated based off of the energy principle. The T was set equal to the time of the tracker video. The KI were all initial values for energy. The F grav is the force due to gravity. F spring is the force of the spring. The net force is equal to the force of gravity plus the F of the spring. The ball's velocity and position were updated but based off of the update equations. L, L hat, and S updated. The spring trail were also updated. And finally, all of the values for the change in energies were updated in order to find the data shown next. This graph shows the computational versus experimental data, in which the red is the experimental and the blue is the computational. You can see that they are relatively similar, except for the red underpredicts the motion of the spring. This could be due to a miscalculation in the period. Also, any human error in finding the data in the tracker software. For the first question and discussion about the energy principle being satisfied, based off of this data shown here, the energy principle is satisfied because the change in energy, which is the yellow line, is equal to 0 consistently throughout the time of the system running. And also you can see that the blue line, which represents the kinetic energy, slightly changes based off of if the spring is stretched or compressed. And the green and red lines, which show potential energy, rotate, which is highest and lowest based off of the stretch and compression of the spring or the change in y of the spring. For the final discussion question, I show the T, or the period of oscillation, for both the x and the y. You can see for the x it is 1.440. For the y, it is 1.472, which is about a 2% difference in these, which would be expected because the formula for the period does not matter the position of the spring. It is solely based off of the spring constant. So these periods are what would be expected for the oscillation.